Wonderful. So that works. Yeah. So welcome, Tatjana. She will talk about you can see it, symmetrized systematic molecular fragmentation as a tool for exploring intermolecular interaction energy. And with this, I would like to hand over to you. The stage is yours.
Okay. Thank you very much for allowing me to present our recent results. I would like to talk about something quite more simple that previous talks, because the whole idea of systematic of molecular fragmentation is to use standard codes for new in order to calculate large molecules instead of developing new codes. So our motivation was that, as usual, that because of scaling of electron correlation method is higher than Hartree-Fock, and on the other hand, we know that intermolecular interactions, which are of indisputable importance for chemists, require this electron correlation methods, even for qualitative results. Then there are many room of improvements for developing or improving methods for calculating intermolecular interaction energy, especially for interaction between large molecules. So one of these methods, which standard method, which are systematic molecular fragmentation, which I will be talking about in a moment, and we just want to show to check if how it applies to intermolecular interaction energy. And so first of all, I would like to introduce the key quantity. So the intermolecular interaction energy is can be defined as a difference between the energy of the complex AB and molecules A and B. One can also define binding energy, but we will stick to the intermolecular interaction energy, which is actually a function of relative position R of molecules A and B with respect to each others. And then I would like to introduce this systematic molecular fragmentation, for which there are many flavors are available in the literature, but we start from the approach of Professor Collins, and his idea was to divide a molecule into groups when one group is like one atom with hydrogens, or a group of atoms connected with double or triple bonds, or for instance, phenyl group is also one group. And then one represents a molecule as a set of overlapping fragments, and these fragments have a predefined size in terms of these groups. So for instance, level of 3 means that we will have fragments of 4 or 3 groups, and of course we have to we are allowed to cut single bonds only, and we separate dangling bonds with hydrogens. And here is a simple example just to show you how this works. And the energy is then composed as a weighted sum of energies of these fragments plus some non-bonded contributions. And with the original formulation of SMF proposed by Collins, there is an issue with branched molecules, because for branched molecules this algorithm is modified, and then we have larger fragments. Then a formal order will allow. So we recently proposed a bit of modified approach when we which strictly preserves this size n plus n formula for also for the branched parts, but we have to introduce some fractional weights of these fragments, and this approach is especially can be especially useful if our fragments, so actually if our groups are not a single atom, but for instance phenyl rings. So treating three or four phenyl rings makes quite a difference for electron correlated methods. For the non-bonded part of the SMF energy, we just use the same approach as of Collins. So I just skip this part. And then let me introduce how we calculate the interaction energy. We just consider this general formula, but we just introduce our energies are just SMF energies. So molecules A and B can be fragmented according to this systematic molecular fragmentation algorithm into a set of fragments with appropriate weights, and a complex AB is trivially actually fragmented into the same fragments. So for this case, this bonded parts cancel each other, and as well as so-called this non-bonded parts, so where both groups belongs to either A or B, and we get the equation for the systematic molecular fragmentation interaction energy as a sum of the interaction energies between fragments from which one belongs to one molecule and the second one belongs to the second molecule, with, of course, appropriate weights. And this approach neglects some small free body terms. So let us see how this approach works. And it should be emphasized that this approach does not require any extra programming, because this interaction energies can be just calculated with the standard codes. So the fragmentation have been made with the homemade program written by Emran Masumi-Feshani, who is my PhD student. The calculation of energies will perform it with either with MolPro or with Psi4. And this fragmentation code written by Emran makes also inputs for MolPro or Psi4 and Q scripts for computer clusters. And we use the third level of fragmentation, which has been proved to be good enough for practical application in our previous work. So our test molecule, main test molecule, was 9 mer of glutamine. And in one case, we also used 9 mer of glycine. And we tested interaction of this molecule with small, actually one atom or water. This SMF-free approach produced about 100 fragments of like these two. So they are all of more or less the same size. And so see that for electron correlation methods, such fragments are not problems, even for advances like CC-dependent LST method, canonical ones, while calculation of CC-dependent LST for the original molecules can be difficult. Okay, so we were using two configurations of this test artificial molecule with different and we move water or neon away from the molecule just to test the dependence on distance. Okay, so let us look at the results. So first we make the calculation on the MP2 level, and for this 9-glutamine and neon. Here we have the correlation energy. Actually, the correlation energy part of the interaction energy calculated without SMF approximation and with SMF approximation. And here are, so one can see that these numbers are quite similar to each other, and the percent error is at most one or at most a couple of percent. Oh, that's me. So while for the Hartree-Fock part of the interaction energy, the good agreement appears actually only for the smallest two distances, while for larger distances the error becomes larger. So actually here also the value of this interaction energy becomes large, becomes small, but it is still not negligible, and the error is not good. So let us see if this behavior preserves for the polar molecule like water, and one can again see that okay, there is Hartree-Fock energy error increases, but the error of the correlation is actually small, stable small. So here this correlation energy just goes through zero. So here this is why we have this minus 12% error. So this is the analysis of just supermolecular energy, which we can just divide into correlation part and the Hartree-Fock part. So let us see how does it look if we divide the partition the interaction energy into the using the symmetry adaptive perturbation theory method. So here we have always the subcomponent in Hartree's, and in parentheses this is the percent error with respect to the SMF sub-zero with respect to the total sub-zero for a given component. So what one can see? So first one can see that the dispersion energy behaves very well. So this is the percent error is actually almost always below 1. Also dispersion energy, so-called exchange dispersion energy, is also small. The error is also small actually for all cases when this exchange dispersion energy has any importance, because for large distances it's just quite zero as all exchange energies. But the induction energy, and especially the electrostatic energy, behaves poor. It for larger distances we got larger percent error, which are actually inconsistent, which is consistent with the picture presented by the supermolecular MP2 energies. One can also note that we know that asymptotically Hartree-Fock energy is represented by electrostatic 1, 0 and exchange and induction 2, 0, while as MP2 correlation interaction energy is represented by dispersion 1, 0, 2, 0 and a smaller term exchange electrostatic response electrostatic 1, 2, 1. This second number denotes the order in the fluctuation operator. So this was the situation for water, and for linear 9 blue. Then we can see also the we just wanted to see if the same picture we can get if actually more units interact with water well on the same footing. So we invented some sort of strength of bent 9 blue molecule, and we see here that we have actually more or less the same picture. But here with the difference that now the induction energy behaves poorly, and electrostatic well a bit better, but also errors are larger than we would like them to be. But the dispersion energy is again behaves perfectly. So let me show you actually this is actually the same example, but the same situation, but for the glycine 9 mer of glycine, where we have exactly the same situation for dispersion. So the error below 1% in all cases, and induction also that it starts to behave more or less correctly also for small distances from the n-mer of glycine, but for larger distances the error becomes well stably large, and we have a bit better dependence, actually better dependence for electrostatic, but in general this induction is not well behaves not good. Okay, so summarizing, I hope we see that I showed the behavior of the modified systematic molecular fragmentation algorithm, and for the intermolecular interaction energy, I divided this intermolecular interaction energy into the electron correlated part and the Hartree-Fock part. The electron correlated part is reproduced very accurately on the given level of fragmentation, which is SMF free. But the Hartree-Fock part is reproduced not as well as one can wish. And the sub-partitioning shows the culprit for the situation, and these culprits come from these subcomponents which are sensitive to the polarization of electron clouds. So this is the second order induction and first order electrostatic, and these are exactly these components which are make a part of Hartree-Fock interaction energy according to the well-known paper of Hałasiński and Szczęśniak. On the other hand, the electron correlated contribution, which is mostly dispersion, this 2-0 dispersion. So this means that its order of fluctuation operator is very well reproduced by this SSMF free approach, and one should emphasize that this electron correlation part is much more expensive in the computational term than the Hartree-Fock part. Therefore, one can use a sort of hybrid method where the intermolecular interaction energy is calculated as a difference of Hartree-Fock energy is calculated for whole molecules, and where this SF or SFMF can be is used only for the electron correlation or electron correlated part. And so this, with such approach, and we are actually this work in progress, the calculation of this electron correlated part of the interaction energy with methods like CCSD parenthesis T can be feasible and actually quite easy. And such calculations with made for just one large molecules can be, well, are very difficult, although now we know from our previous speakers, maybe not impossible, but quite involved computationally. Okay, so I would like to well, acknowledge the money which comes from the National Science Center of Poland, and for the computer time on mostly on Prometheus cluster, but also on PRACE, it's a grant on Eagle cluster in Poznań. And I would like to also to show my collaborators on this project, and my collaborators is my present student, graduate student Emran from Iran, from Shiraz, and Michał Chojecki, who is my former graduate student. So with this, I would like to thank you for your attention.
Thank you, Tatjana, for this interesting presentation. So we still have time for a couple of questions. So please go ahead. Are there any questions? That does not seem to be the case yet. So maybe I can start with the one question. So on slide 11, where you looked at the interaction energy as a function of the distance, I noticed that there are some sort of oscillations in the error as you go along the.
One moment, I have to show the. Oops. Slide 11.
Yeah. Yes. So here, yeah. So. Exactly, in this one. So here the error seems to be first positive, then negative, and then positive again. So I did not quite get it. So but I guess in your SAPT analysis, so what is sort of the reason for this behavior, so that the error sort of oscillates as a function of this distance between the neon atom and the chain of this?
Yeah. So okay, so I have not don't have the SAPT. Okay, actually, I have a sub-zero for this case too, but not here. Well, actually, I haven't analyzed this so deeply for the moment, because I was just satisfied that the error is small, and well, so I think that errors of this of this size, well, should be accepted for methods like systematic molecular fragmentation, because, well, this is actually the disadvantage of such method, is that we are not supposed to converge to the exact value. This is because we have this artificial hydrogen atoms. which we, because we have to saturate our bond, which we break. So I would not go so deeply into analyzing of this small difference, but I will, as you saw, I think I have to analyze this maybe with some higher order SAPT, because for the moment we are using only SAPT0, which is the quickest to obtain. But actually, as I showed you here, in order to analyze the SAPT0, analyze MP2 interaction energy in terms of SAPT, we have to use not only dispersion is 2-0, but only also electrostatic response 1-2. And in Psi4, for this one can calculate the so-called level SAPT2, which is more expensive. Therefore, we are still working. We are still calculating this extra terms. But maybe this electrostatic will show us something. So for the moment, I have no answer, definite answer on this.
Okay, so I see there's thanks. So I see there's one more question by Georg Janssen. So I think we can still take that one.
Hello, Tatjana. Thanks for your talk. That's a good perspective for doing calculations on larger systems. The methods you have shown us, MP2 and SAPT0, treat the correlation and dispersion energy in kind of an additive formula. So I wonder a bit whether the additivity is still true if you change your correlation method to CCSD or to a ZAPT variant including orbital response. Did you test that already?
Well, we started to test this, but I still don't have definite conclusions.
Okay.
For this, but this we have this in our to-do list.
Mm-hmm. Okay, thank you.
But we have actually done some CCSD parenthetic calculations for the just to calculate correlation energy on CCSD, for instance, but of CCSD level with SMF and just non-SMF, and the error for the correlation energy was exactly as small as for the MP2.
Okay, thank you. That's good news. Yeah.
Okay, so with this, I would like to thank Tatjana again for this presentation and all the speakers of the sessions of the session, wave functions, correlations, and scaling. So I think we have seen impressive results and tremendous progress in that regime. And with this, I would like also to close the session and thank you for your kind attention, and hope to see you later in this in the early afternoon, at least in Europe,